Hello and welcome back. Today I want to continue talking about power supplies by looking at a somewhat complicated but still important measurement. It's not all that common to perform this for hobby circuits, but it's quite an important step when a high reliability circuit is needed. Most often, you will be doing this for switching converters, but sometimes it's necessary for LDO type linear regulators as well. What I'm talking about, of course, is measurement and evaluation of the loop response. So, if you're curious, then keep watching. Now, in all previous episodes in this mini-series on power supply measurements and behaviors, we discussed, to an extent or another, the impact of the feedback loop, the control mechanism responsible for keeping the output of the supply at a fixed voltage value. Now, when looking at things like static or dynamic accuracy, you are indirectly measuring the feedback loop by observing its corrective action when an external perturbation is applied. In contrast, the measurement we will be looking at today is the direct way of measuring the loop's performance by interrupting it and directly injecting a measurement signal into it to see how it reacts. Now, this is not a test that replicates a real-life behavior or situation, but rather it's performed strictly to get a numerical and quantifiable measure of the power supply's performance by analyzing its bandwidth and stability. Let's start off by talking about what it is that we're trying to measure. So, in its most basic form, a power supply is comprised of a power stage, the bit that lets energy pass from input to output, a reference voltage, a feedback divider network that senses the output voltage, and an error amplifier that compares the output to the reference and based on this drives the power stage in a way that ensures the output voltage is maintained at a fixed level. It's a simple negative feedback closed loop system. So what it is that we're trying to measure about it? Well, I will focus on two main things today: bandwidth, or the reaction speed, and stability. And to do that, let's look at an example. At a point in time, we have a fixed load on the output, current is being allowed to pass through the power stage because of the control signal, and the output voltage is stable. This is what you can call a static operating point. Now, for whatever reason, the output load suddenly changes, so it decreases. Because the information does not pass instantaneously through the circuit, it takes a while for the power supply to react. So in the very first moment, the power stage is letting the same energy pass through, so the output voltage increases. Only after a short period of time, the error amplifier reacts and tells the power stage to reduce the output. And from here, it takes again a given amount of time for the power stage to, well, react. Now, the next thing to observe is the magnitude of the change. Ideally, you want the output voltage to perfectly stabilize to the previous value. However, if the reaction to the perturbation is too strong, and it's coupled with large time delays in the system, the output will end up dropping too much, which will lead to the error amplifier again giving the order to increase the output voltage again. And this can lead to an oscillatory output, something that you definitely don't want. Now, to an extent, you can observe how stable the loop is by applying a load step. However, the result of this test will be highly dependent on the exact load step that is applied, and it will not really tell you how stable the loop is and what can be done about it. So, the main thing that you're trying to measure when performing a loop transfer function characterization is to observe the behavior of the supply over a wide frequency range, and to get a quantifiable indication of just what's going on. The general idea behind this test is quite simple. You take your power supply, you interrupt your feedback loop so that you can inject a test signal into it, and then observe the variation in the output. What you're looking for is the reaction magnitude of the system, how strong of a reaction the circuit provides, as well as the time delay between the moment when the signal is injected and when the response appears. And this is recorded as a phase shift. So in essence, you will end up creating a Bode plot that represents the response of the power supply over a specific frequency range. Now, even though the graph in its entirety is a valuable representation of the power supply's behavior, the most important point on it is the gain crossover point, the point where gain passes through unity. The frequency at which this point happens will dictate the speed of the loop. The higher the frequency is, the faster the power supply can react to a perturbation. So if you can change things, you want this point to be as high as possible. But the other important information is the phase shift at which this crossover happens. In essence, if your output to input phase shift is 0 degrees, rather than having negative feedback, you have positive feedback. You don't want positive feedback. So you want to have a positive phase shift value, and the higher the value of phase shift, the more stable the supply is. So the phase shift at this specific point is also known as the phase margin. A general rule of thumb is that it should be above 45 degrees. But in more conservative designs, values above 60 degrees are required. In general, if you want to improve the phase margin, you will end up reducing the crossover frequency. So the power supply compensation will generally become a compromise between reaction speed and stability. Now, another important point on the graph is the moment when the phase does pass through 0 degrees. Ideally, you want to have subunity gain at this point, but the lower the gain, the better. So this is referred to as the gain margin. Again, as a rule of thumb, values lower than -10, -15 decibels are recommended. Now, today's focus will not be on how to change the response of the supply, but rather just to be able to measure it accurately. So next, let's see how we can practically extract this response curve, starting off with the circuit simulator. LT-Spice, of course. So, to keep things simple, let's start by looking at the basic linear regulator. So I have the generic test fixture for this analog devices part. You can find it in the LT-Spice library. And this is an LDO type regulator. So this is outputting about 3 volts. Now, if we interrupt the loop and directly inject a test signal into it, well, this won't really work. So we can see our injected test signal, but the output is at a completely different value than it was before, so it used to be 3 volts. And well, we can't really see the effect of the test signal in this output. The main issue that we have is that the static operating point is not ensured by this specific setup. So the power supply is not stable even without the injection of this test signal. Now, even if you could stabilize the loop, the other problem is that you need to keep strict control on the output. So especially at low frequencies where you have a lot of gain, you will need to inject very small signals. So the way around this is to inject the test signal into the loop directly without completely interrupting it. So to have the signal source connected into the loop interruption. This way, we can monitor the injected signal, but also the output response, which is centered around the 3 volts DC operating point. Now, by implementing the injection this way, the injected signal and the output result difference will always be more or less under control, since the difference of these points is the exact injected signal. So if we look at the 2 points, so before and after the signal source, we can look at the loop response based on the 2 curves. So the amplitude ratio between the 2 curves will be the magnitude at which the loop amplifies, and based on the timing between the 2 signals, we can determine the phase shift of the loop. Now, another thing to mention is that your practical signal generator is usually referenced to ground, so you can't practically connect it like this. Rather, you will be using a isolation transformer, so something that takes the ground reference signal generator and makes it floating so that it can be connected directly into the feedback loop. Finally, to impact the converter's behavior as little as possible, a small value resistor is usually placed in parallel with the transformer, close to the physical regulator. Now, before moving to an actual measurement, there is one final thing to discuss. Where should you break the loop? I mean, what should be taken into account when choosing a point of signal injection? There are many points to choose from, but not all of them are equally recommended. So in theory, you could break the loop anywhere, either in the power stage, the signal driving the power stage, or the feedback input. But there are a few important considerations to take into account. First and foremost, the breakpoint needs to be accessible. In most cases, the error amplifier output is integrated, so that won't do. Next, the point needs to be in a linearly behaving part of the circuit. So you don't really want to interrupt the gate of a switching converter. So this usually leaves the feedback resistors as the only access point. But even here, we need to make sure that the measurement does not affect the overall behavior of the supply. So it's recommended that one side of the break is in a low impedance node, like the power supply's output. Since we are adding the small value resistor, this low impedance point is kept when connecting to the rest of the circuit. So the most common interruption point is above the upper feedback resistor, which connects to the output capacitors. Final thing to mention here is that if you have other components, like some capacitors around the feedback resistors, these are also part of the feedback network. So the signal injection point should not bypass these. With this sort of setup, the interruption needs to be between the output and the rest of the circuit to get a correct result. Finally, let's try to perform such a measurement and see what sort of results we can get. For that, I have the soldered test board with a boost converter, and in preparation for the measurement, I already interrupted the feedback path and inserted the 33 ohm resistor. This is where the signal transformer will be connected to, and also where the measurement probes have low noise connections already attached. For this measurement, the power supply of course needs to be supplied from supply voltage, and the load needs to be added on the output. So both of these need to be monitored, and it's important to take into consideration that the power supply loop will have different behaviors under different conditions. So it's important to perform this test under multiple load values and input supply voltage values. Now, specifically for the loop measurement, I'm using an oscilloscope with signal generator coupled together in Bode plot mode. So you could of course do the measurement manually by injecting signals step by step and then measuring the amplitude and phase ratio. But if you have a piece of equipment that can do this automatically, it just saves a lot of headaches. Now, before proceeding to the actual measurement, it's important to check the behavior of the supply when the test signal gets injected. So if the test signal that is getting injected is too small, it will be too noisy and very difficult to measure, so you can barely see something in the yellow line. And on the other hand, if the signal is too large, then it will end up getting distorted. So what you're trying to look for is nice sine waves on both channels, so on both sides of the isolation transformer. If you don't have that and you have something like this, most likely you will end up getting some false results. So it's important to find a signal amplitude value for which the measurement can be done without distorting signals. Now, another point to make about this injected signal is that it will usually be different for different frequencies. So at relatively low frequencies, the power supply has a lot of gain, so you will be working with larger signals. As you move to high frequencies, the gain drops, so you will be working with slightly smaller values. So if we now go to the actual measurement, so I have my oscilloscope set into Bode plot mode. I'm doing a simple type sweep, which means that we have a constant amplitude of injected signal, 200 millivolts in this case, and it will be going from 10 Hz to 300 kHz. And if we run the measurement and wait for it to finish, we can have a look at our Bode plot. So we can see a relatively flat gain plateau going up to a certain frequency, after which it drops off. So we start with about 40 something decibels, and then our crossover point, so where our gain reaches the value of 1, is somewhere between 80 and 100 kHz. Now, unfortunately, at this frequency, we have a very small phase margin, so only 20 something degrees, so it's not the most stable power supply. But another thing that can be said about this measurement is that it's not very clean, so it's quite bumpy. And the reason for this is the injected signal. So I used a flat signal value for every single frequency. Now, some pieces of equipment will let you inject variable signal amplitudes. So one of the things that we can do is inject relatively large signals at low frequency, so go with 400 millivolts, and then drop down to relatively small signals at higher frequency. So this should prevent the injected signals from getting distorted, and it should help us get a cleaner result. So if we run the measurement like this, we are getting a cleaner result, so the gain doesn't jump around as much. It's a far more stable line. And if we look for our crossover point, it's again in the same 100 kHz region with the same phase margin of about 20 something degrees. So this should be a more accurate result. And anyway, if you want to get a clearer picture, you can always perform more test steps. So right now I only have 10 points per decade, but more can be used. Now the final thing that we can do to confirm our measurement result is to indirectly measure our crossover point by applying a load step. So when you're applying a sudden change in output current, the power supply will have to react to this, and the way in which it reacts can tell you a thing or two about your crossover point. So I have this extra resistive load, which I will suddenly connect to the output, and we can trigger on this event, and what we can see is that the output ends up oscillating, so indicative of our very low phase margin. And if we use our cursors, we can see the frequency of this oscillation being 109 kHz. So when a load step gets applied, the power supply will end up oscillating if there's very low phase margin, and the frequency of oscillation will be the crossover point. So this is an indirect way of confirming our previous measurement. In the end, the loop response measurement is a rather complex test that requires some specialized equipment, but it will offer valuable insight into the inner workings of your power supply. Namely, how stable it is and how fast it can react. Especially if you're adjusting the feedback compensation, having a visual wide frequency representation of the supply's behavior is an invaluable tool. Now, even though in most modern supplies the compensation is internal, so there's not much to adjust anymore, you will still sometimes need to do this test to confirm the circuit meets the design stability requirements. And with that said, hope you got some useful information after this. Leave your thoughts in the comments. Thank you for watching. Be sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.